Sebastian?
Yes. Okay,
Okay.
Thanks for the presentation. I am a doctoral student in Tromsø under the supervision of Kodian. And today I want to present two of the main projects that I've worked on the last years. And I hope that I can split the time equally to two projects. So the common features that we have a group G acting on the real polynomial ring in n variables. And the group is either the symmetric group or the hyperoctahedral group. So the hyperoctahedral group is the wave product, which is the semi-direct product of the cyclic group C2 and the symmetric group. And it acts then on the polynomial ring by permutation of variables like the symmetric group, but also by switching of signs. That means that xi can be mapped to minus xi. And the invariant polynomials that we consider are then symmetric or even symmetric. And part one is joint work with Philippe Moustrou, Cordian Rina, and Hugues Védur. We have an archive preprint available, and we consider ideals of symmetries of this hyperoctahedral group Bn. And this work uses a lot of Young tableaus and combinatorics of them, but in the end, we have some concrete complexity bounds and a number of coordinates of elements and the rarity of such an invariant ideal. And the second part is something that you heard already about last Monday when Craig mentioned some of the results. And there we consider cones of even, symmetric, non-negative, and sums of squares polynomials uniformly in the number of variables for a fixed degree D. And then we want to study the behavior for n goes to infinity. So as you know, there's a result of Craig, which says that if you have a fixed degree D, then the PSD and the SOS cones do not converge to the same limit for n increases. There are some asymptotic bounds, and actually the ratio of these cones grows. So what is now in the equivariant setting? That's something I want to speak about, and we will see, but it's also something that you heard about last Monday, that the limit results differ a lot from the ones where you have only finitely many variables. And this is work in progress together with Jose, Craig, and Cordian. So let's start with part one. The motivation is the following. So maybe you know that for the symmetric group Sn, the evil representations are called Specht modules, and they correspond to integer partitions of n. For the hyperoctahedral group, now the irreducible representations are also called Specht modules, and they correspond now to pairs of partitions, which we call bipartitions. And in both cases, the irreducible representations can be constructed with Specht polynomials. And both cases go also back to Wilhelm Specht from the 1930s, although the Sn case is well more known than the Bn case. And when we now consider Bn, then it is the case that some things are more complex, since we have way more bipartitions than integer partitions. So the generating function is actually the square root of the generating function for integer partitions. And there exists many partial orders on the set of bipartitions of n. There also exist many on the set of integer partitions, but there the dominance order is important. So we try to find something analogous to bipartitions. And we want to relate some results from Sn to Bn and try to find analogs. And this has, as I said, applications in solving symmetric systems of equations, but there are also inner mathematical relations to combinatorial commutative algebra or to combinatorics of subspace arrangements, since these rarities of these invariant ideals, they are unions of subspace arrangements of type A or type B from the root systems. So let's start with some basic definitions here. So I already mentioned partitions. These are non-increasing sequences of positive integers, and their sum should be equal to n, then we call it a partition of n. And we represent partitions by their diagrams. So this is then the ordered sequence of boxes. And I mentioned the dominance order on partitions. So this is a partial order, and you can compare two partitions of the same integer n, and you sum up every first k entries, and then they should be comparable in this order. And this gives you a posed structure and this is a lattice, and it's non-graded almost for every case of n. So essential for us are also now Young tableaus. We saw these diagrams of a partition, and when we fill the diagram with all the integers from 1 to n, then we call this a Young tableau. And we do not want that they are increasing in any row or column here. And associated to such a Young tableau is then the Sn Specht polynomial. This is the product over all Vandermonde determinants of the columns. So the product over all xi minus xj and I and j in the same column, I above j. Here you see I colored the entries of every row differently because this gives you then different Vandermonde determinants. And then we have the notion of Sn Specht ideals, just the ideals generated by all Specht polynomials of a given shape, lambda, and its affine varieties than the Specht variety. And you see here I use the field R, and these ideals or these varieties can also be defined over any field. That doesn't matter, and many of the results also transfer to positive characteristics. So we are now in the setting of Bn, so we consider bipartitions, and then we associate them with pairs of diagrams, so we have a bidiagram. And again, we have bitableau, so this is then just the filling of this bidiagram with all the integers from 1 to n. And again, we define Specht polynomials. And now I use the Sn Specht polynomial definition here, because the Specht polynomial with respect to Bn is then the Specht polynomial in the first tableau, but now evaluated in x squared, times the Specht polynomial in the second tableau, evaluated in x squared, times the product over all xj, where j is written in the second tableau. And you see this part here is invariant under sign switching, but this on the right-hand side not. And yeah, we also see an example for this specific bitableau here above. And we define now again Specht ideals and Specht varieties associated to this bitableau and the bipartitions. So our investigation or starting point was the following. So there are known results for the symmetric group, which were proven originally by Hyman and Wu, and then extended slightly and independently rediscovered by Moustrou, Rina, and Verdure recently. And they say the following, that integer dominance of integer partitions is equivalent to equivalence of the Specht ideal is equivalent to inclusion of the varieties. And a priori, it's not clear that if we have inclusion of the varieties, then we have also inclusion of the Specht ideals, since they don't have to be radical. And yes, we relate this later, and we see that some Specht ideals are then contained in invariant ideals, and this gives us then these complexity bounds. And another result, so the second one that we tried to generalize, was the following, that the Specht variety can be written as a disjoint union of orbit sets. So orbit sets are then of a very simple form. So they are sets which only contains points, which stabilizer is isomorphic to some subgroup Sn of shape S mu. So it contains then only points with mu1 equal coordinates, mu2 equal coordinates, and so on. And you see here that in this characterization of the Specht variety, you need the partial order, the dominance order, and you need these orbit types. And when we now started our investigation, we did not know if there's a notion of Bn orbit type, or actually there is not in the literature. So we had to look for one of them. And we also had to look for a partial order, which encodes our structure here. And we did some calculations in the beginning and calculated posets for n equal to 6. So we calculated the ideals and checked when are they contained in another. And then we had some guess on the partial order, namely the following. So you have these bipartitions, and then you compare them in the following way. So these two equations must be satisfied for every k. And the first is actually a dominance order on partitions, and the second one not. And yeah, this is another way to write it would be the following. So you take a bipartition lambda mu, and you make it to a sequence lambda 1, comma mu 1, comma lambda 2, comma mu 2, and so on. You do the same with the second bipartition. And then they are comparable in this partial order, even only if the dominance order in these sequences is satisfied. But this is very different from the case of integer partitions, because not all the results generalize, which we will see. So we have to do some classification there. But we have a poset structure, and we see here examples of bipartitions which are comparable. And this is, we check whether these two equations are satisfied for every k. And we also see that it's not a total order, because there are bipartitions which are not comparable. And this partial order is not self-dual. This is different from the integer partitions. It's not graded, and it's not a lattice. This is also different from integer partitions. And we prove that the spaced ideal and variety inclusions are captured by this partial order. Here you see such a Hasse diagram. So you know the Hasse diagram definition maybe from Arne's talk 2 days ago. You don't have to read what is written here on the vertices, but you can just see that for n equal to 4, you have already many elements in the poset. And you can see that it's not a lattice, because these two blue elements are not comparable, but they don't have one element which they cover. They cover, but they have two elements they cover, but there's not one unique element which they cover. And we show then the analogous result that we have then ideal inclusion and variety inclusion captured by this partial order. And we don't know if these ideals are radical or not. So our proof goes the following way. We prove constructively that if you have dominance of these bipartitions, then you have ideal inclusion. And therefore, we classify first all the covering cases in this poset. And then for every covering case, we give a concrete way how you can obtain the spaced polynomials of the smaller partition from the spaced polynomial of the larger partition. Then we immediately obtain the variety inclusion. And then to go from here to the dominance of the bipartitions, we do some counting arguments. So we fill some diagrams, and then we see that this gives you then this dominance order on the bipartitions. Now I want to speak about the orbit type. I mentioned it already for the symmetric group. So here we observe that any element in the vector space Rn is of the following form: lambda 1 copies of x1 up to lambda k copies of xk. And now we assume that these lambda i's are ordered non-increasingly, and this gives us a partition, and this is the orbit type of the element. And what do we know for Bn? So for Bn, we should group it in two pairs, into the lambda part and into the mu part. And we can switch the sign. So maybe 2 and -2 should be identified. But 0 is a little bit special, since the orbit of 0 is just a singleton at 0. So how can we group this now into bipartitions? And we see every element can be written as t copies of 0, and then again lambda copies of some other elements which are strictly positive. And we have, in the Bn case, way more bipartitions than orbit sets. So many are empty now. What are we doing? So we construct the associated orbit type as a cut of the Sn orbit type. Namely, we fill a diagram with this coordinates such that they are ordered increasingly. So every row has up to sign the equal columns. And then we go to the column where you have zeros. So we have 2 zeros here, so they are in this column. And then we cut out now vertically everything which is right where the 0 ends, and we put it onto the right-hand side. And this gives us then a bipartition, and formally we define them as t-cuts, and just the bipartitions which arise as specific t-cuts are then encoding non-empty orbit sets here. And we obtain a set partition now of Rn. Here we see an example of R3. So we have 10 bipartitions, 7 have non-empty orbit set. And what is nice here is that we get some information about the zeros, because when we now want to solve symmetric systems of equations, we can immediately use that many of the coordinates must be 0, and then the dimension shrinks. But also we know that some coordinates are equal. And there are also bipartitions which have an empty orbit type. And we have also an analogous result to this description of the Specht variety, now using our partial order and this orbit set notation. And the proof of this variety description can actually be seen as some generalization of the earlier result, that when you have inclusion of Specht varieties, then you also have this dominance of integer partitions, bipartitions. And I told you that we had to classify here the covering cases for bipartitions. For integer partitions, this is something already known since the 70s, done by Prilavsky. And for integer partitions, you have only one single case. So actually only this type 1 case. But now for bipartitions, you have 4 cases. And here something is a bit tricky, that you must move many boxes simultaneously at the same time. In type 3 or type 4, you take a column from the left and you take the column to the right, or the column from the right and take it to the left. And you always go down one row or you stay in the same row. And yes, so this picture tells you already everything you must know about those covering cases, because the proof is quite formal. It's a quite long case distinction, but there's not more information in this theory, more in the proof, I believe. And this condition 1 here is actually very important, because it makes sure that you cannot insert this box somewhere else before. You cannot insert this box on the right-hand side. And here we see now an example of a non-covering. And on the left-hand side here, and on the left-hand side here, we have partitions which cover each other in the dominance order. But this is not a dominance now in bidominance, because with operations of type 3 and type 4, we can construct something which lies in between. And our application is then the following. So you have given any B-in invariant ideal, and not only in the reals, but in any polynomial ring. Then under some sparsity condition, we have that we can say one Specht ideal is contained in this ideal. And the sparsity condition is the following. So you take any polynomial, any polynomial which is contained in I, and then you could consider only the leading term of this polynomial. And then you consider any monomial in this leading term, and then you need some freedom. So this monomial should have only very few coordinates, or a little few coordinates, and then you can do some operations with the symmetric group or with the hyperactivity group, and you construct a Specht polynomial which is contained in the ideal. So from this we know that the whole Specht ideal, because it's invariant, is contained in the ideal. Then we know that the varieties are contained in another, and we can obtain complexity bounds on the structure of the zeros. And I prepared an example, so in only 4 variables, and let's assume that this polynomial here is contained in the ideal. Then we know under the sparsity condition that one Specht ideal is contained. So we have one inclusion of the varieties. And this gives us then an upper bound of 5 different structure of zeros of the coordinates. And we see actually that it's a relatively good upper bound, because 3 of these different structures occur in the variety. And the good thing is that we know that many variables are 0 here. We also have an application in representation theory, which says that this group Bn is a bit special, and something fails for other groups, also for finite reflection groups, which is still true for this Bn group. And another thing independent of this representation theory here is that this variety inclusion above, or the ideal inclusion, gives you also bounds on the dimension of the coordinate ring, because combinatorialists study a lot, or study the number of standard bitableaux. And from this, you then immediately know the dimension of the coordinate ring of an invariant ideal. And I mentioned that we don't know if these ideals are radical or not. We believe that they are, and we also believe that the spaced polynomials contained in such an ideal form a universal Grobner basis. And this is, first because it's true for the symmetric group. This goes also back to Hyman and Wu, and then rediscovered recently by Murai, Uchuki, Koji. And yes, so this spaced polynomials for Sn and for Bn, they are very special. They encode the irreducible representations in a minimal way. So we believe that the conjecture is also true for Bn. We did calculations for n up to 6, then the calculations were not feasible any longer. And also we try to adapt their proofs, but this doesn't work. So none of the proofs can be so easily adapted because they go by induction, and then you must add one box in the tableau, but for us, it could also be on the right side, and then the degree would be too high. So this cannot occur for integer partitions. And also these two proofs rely very heavily on the fact that not that every orbit type is non-empty, but for us, we have plenty of empty orbit types. So it seems that we cannot use their proofs. So this was part 1. Do you maybe have one question or 2 questions to part 1? Otherwise, I would continue.
So I don't see a question. Somebody wants to speak up?
Okay.
Please go ahead, Sebastian. Thank you.
Then let's continue with part 2. So on Monday, Craig told you about the connections of extremal combinatorics and real algebra. And he was speaking a lot of the power sum results, where we consider functions in the power sums. And here I want to show you now more of the sums of squares and non-negative results that we obtained from this study. And the notation that we use here is the following. So we consider forms which are invariant, and then we denote the set of all forms by h and d to the power g in n variables of degree d. And then we consider the SOS and the PSD set of these invariant forms. And as you all know, that goes back to Hilbert from 1888. There are only very few cases of equality between the PSD and the SOS cone. And when you consider invariant situations, then this can differ. So this classification does not necessarily remain true. And prominent examples for the hyperpolyhedral group were found by Harris. For ternary octets, you have equality, and also for quartics in any number of variables. But for quartics, the vector space has only dimension 2. So this follows already from the dimension there. And it turned then out, that was proven by Charugol, Salma Kuhlmann, and Pusuesnik for the group Sn and for Vn, that these are the only non-trivial cases of equality. And so something that we asked us is, what happens now if n converges to infinity? Can we say something about the limits of these symmetric and even symmetric non-negative polynomials and sums of squares? So when we define the limit, we use the notion of symmetric functions. A symmetric function is like a symmetric polynomial, but it's not now a polynomial, it's a formal power series. So it is symmetric with respect to the group S infinity, and it is product or linear combination of products of these power sum functions. They're analogous to power sum functions, the symmetric polynomials. And this ring of symmetric functions can be constructed as the inverse limit of rings of symmetric polynomials, where you consider the following transition maps. So you take any symmetric polynomial in many variables, and then you set the last variable equal to 0. And what you obtain is then a symmetric polynomial in less variables. And yes, so by this, we also have that when we consider the set of forms, these have the same dimension, because you can use the power sums or products of power sums of vector space bases here. And then now we consider degree D in the symmetric case or degree 2D in the even symmetric case. Then if you have power sum PD plus 1, this doesn't help you. So it's not any longer in the basis. So we have stabilization of the dimension for n greater or equal to d. And then we use these transition maps now as isomorphisms. And then also the ring of symmetric functions of homogeneous symmetric functions of degree d has then the same vector space dimension. And here I mentioned the power sum function pk, but we also use the elementary symmetric polynomials or the elementary symmetric functions. And this can be due since they are the Newton identities, which provide polynomial relations between the elementary symmetrics and power sums. And sometimes it's more, it's more useful to work with power sums, and sometimes it's better to work with elementary symmetrics. I will speak a bit about that on a few slides. And under this identification, we have inclusions now. So when you increase the number of variables, then you have some shrinking or some decreasing of the cones of PSD and SOS forms. And this is because, yes, if you set the last variable equal to 0 of something which is non-negative, then it's still non-negative, or it's still a sum of squares if it was a sum of squares before. So because we have now this decreasing change, we don't know a priori about the limit. So maybe the limits are equal. And we define now the limits of these symmetric and even symmetric sums of squares and PSD cones as the intersections of all of them for finite number of variables. And it turns out that they are also really limits in the sense of Kuratowski convergence for convex sets. This means that the limit superior is equal to the limit inferior of these changed and finite number of variables. And these limit cones are again convex cones, which are full dimensional and pointed. So we can use again convex geometry to study those cones. And this is now very much related to studying the Vandermonde map, which is in n variables of degree d, the map whose components are the first d power sums, and we consider its image m and d. And we also consider its image at infinity, because these images now form nested increasing sequences. And why are they so much connected? Because we can construct the dual to the limit cone based on knowing the limit image of the Vandermonde map as the convex conical hull of the homogenization of this limit image. And the same is then true for Bn. So there we consider the even Vandermonde map, which contains the first the even power sums, and then we consider its image, now denoted by nd, and yes, we have the construction of the dual to the even symmetrics at the limit. And I said that Arnold and Kostov studied this Vandermonde map, and this goes back to Arnold in the general case of the Vandermonde map. There he classifies the boundary in finite number of variables. And he does so in a very much related sense as what Arne told us about 2 days ago, based on knowing the multiplicity vector of coordinates, which are then mapped to non-singular points of the coordinates. And we adapt this proof from Arnold to the even symmetric setting, and then we can also characterize the boundary now in finite number of variables there. And there are 2 cases. So I distinguish here again between the even and the odd, because there the situation differs a little bit. And yes, so what Greg already mentioned is that we try now to give also a generalization to the limit. But to the limit, it seems that we need different techniques than Arnold's. This doesn't transfer so easily to the limit. And this multiplicity vector characterization actually can also be used to explicit parameterizations of the boundary in the plane, where we now restrict to P2 equal to 1. So these are all homogeneous, not homogeneous, but weighted homogeneous functions. So let's restrict to P2 equal to 1. And then we can give parameterizations for n finite and for n infinite when we consider P2, P4, P6. And this is an image that you saw already on Monday in Greg's talk. So he labeled also, I think, the curves on the boundary. So what we see here is n equal to 3 and n equal to 20. And we have in general then n many curves on the boundary, smooth curves, and the upper part grows. So this only grows in the number of variables, while everything which was on the lower part of the boundary stays on the boundary if you go from n to n plus 1 variables. And when you go then from n to n plus 1, you add in addition another smooth curve at the lower part here of the boundary, and then you prolong the upper part of the boundary. And yes, here it looks already quite smooth for n equal to 20, but it's never smooth actually. And what you might see from the picture, but this is of course not a proof, is that this limit image has, which you restrict now to p2 equal to 1 for compactness, has countably many infinite isolated singular points, which are points on the rational moment curve and its limit. And those are precisely these cusps here on the boundary. So we don't have a semi-algebraic set any longer if the degree is at least 3. And this we then obtain immediately from the corollary for ND or N3, and then also for its convex conical hull for Sn and for Bn, if we then consider some intersections. And this gives us a strict inclusion between the limit SOS and the limit PSD cone when the degree is at least 6. But then there's still the case of symmetric limit forms of degree 4. And there we can actually use a result of Kostov, because Kostov studied in degree 4 the limit of this Vandermonde map, but not in the power sums and the elementary symmetrics. But using Newton's identities, we can go back to the power sums. And we combine Kostov's results, and we study with some symmetry reduction techniques the dual to the SOS cone. And this allows us to verify that this set, the dual to the SOS, then set minus the dual to the PSD is non-empty. And so why do we know from the non-semi-algebraicness the strict inclusion? And this is because we can verify, or we can also explicitly write a spectral heatful description for the dual to the SOS cone at infinity as a limit with symmetry reduction to the ones and finite number of variables. And this result of Kostov actually gives a way to construct test sets. Those come on the next slide. And based on this test set and some arguments with using discriminants of univariate polynomials, you can construct examples of polynomials which have uniform variables. So they actually limit polynomials and are limit PSD, but not SOS. And this is one such polynomial. And it turned out that already for n equal to 4, it's not a sum of squares. And this we verified in Macaulay 2 using the sum of squares package there, and then doing some rounding. And this is the minimal case, so it's never a sum of squares in any non-trivial case there. And I mentioned these test sets. So that's also something Craig mentioned, I think, last Monday briefly. So we are in a situation where we consider homogeneous polynomials or homogeneous symmetric functions. So such a homogeneous polynomial is non-negative, even only if it's non-negative on the probability simplex, because now we assume that it's also even symmetric, so we can restrict to the non-negative orphan. And then we require that the sum of, that it's in the probability simplex an element by homogeneity. And here now you see that I write elementary symmetrics instead of power sums. And we evaluate the elementary symmetrics in x squared and not in x. And this is because we have the hyperoctahedral group and not the symmetric group. And if now a homogeneous elementary symmetric polynomial is a linear combination of products of elementary symmetrics, and only E1 occurs non-linearly in this description, then this polynomial is non-negative, even only if it's non-negative on the convex hull of the image of the elementary symmetrics on the probability simplex. But then it's also non-negative, even only if it's non-negative on the vertices of the convex hull. And these vertices have been studied in extremal combinatorics before by Bolobas. And he did this in the plane, but it then was shortly afterwards generalized to more general to arbitrary linear combinations of elementary symmetrics. And this gives you then test sets to test if a polynomial is non-negative or not. And then this is different from the even symmetric case. So you have symmetric homogeneous functions, and now this works only in the limit, not also in finite number of variables. And then based on the work of Kostov and our results in the dual to the sums of squares cone, you can also give a test set to test non-negativity or SOS for such limits of symmetric polynomials of degree 4. And you have many copies of discrete lines for non-negativity, and you have many copies of this intervals for testing SOS. And now I want to talk about the difference between the power sums and the elementary symmetrics. So I mentioned the Newton identities, and when we now consider finite D, then we always have that the images of the power sums and then the elementary symmetrics are equal up to a polynomial diffeomorphism. And here I use now Rn, but we could also consider R greater or equal to 0 in the non-negative orphan when we're in the even symmetric setup. But sometimes it's easier to work with power sums. So in the beginning, you saw that I was a lot in power sums, but now these test sets were in elementary symmetrics. And when we want to make these descriptions of the boundary, then it's simpler to work with power sums because this uses some techniques for optimization. So we use Lagrange multiplier rule, and then the Hesse matrix is way more simpler in the power sums than in the elementary symmetric polynomials. And when we now go to the convex hull, it's better to work with elementary symmetrics, not only because they were studied in extremal combinatorics, so we understand the vertices, but also because this property that I showed you of the test set or the convex hull fails in the power sums. And it doesn't fail for D equal to 3. This is a result essentially due to Joylam-Resnick, where they studied even symmetric sextics, and they constructed test sets, which are then equivalent to this convex hull results and the vertices, but they use very different methods with trigonometric polynomials. But if the degree D is now 4, then the elementary symmetric E2 occurs already quadratic in P4. And then the image is not any longer concavely shaped. So you use the same points, and then this result fails. And it fails for, we prove it for sufficiently large number of variables and also for the limit. So you cannot generalize the test sets to the power sums in such a way. And we mentioned that these limit cones of PSD forms are not semi-algebraic, while in the finite case, you always have semi-algebraicity. And also, that's something Greg mentioned, it follows by Artin solution to Hilbert 17's problem that deciding non-negativity of any polynomial of or rational homogeneous function polynomials is decidable. But when we now consider the multi-symmetric setup, also symmetric functions, and you have now multi-symmetric polynomials functions in k groups of countably many variables, you have access to k copies of the probability simplex. And then deciding non-negativity on k copies of the probability simplex is no longer decidable. And this goes then, just back to Hatimi and Norin, where they provided a theorem on undecidability of graph homomorphic densities. And they deduce the statement from Matija-Visevich's solution to Hilbert's 10th problem that deciding validity of non-negativity of multivariate polynomials on copies of the integers is undecidable. And the key here is that you have copies of the integers or copies of the natural numbers, and for us, copies of the probability simplex. And so we believe that if you don't have copies, so if you have just symmetric functions, then deciding non-negativity is decidable. So that's my last slide. I told you we have this non-similarity argument to show that the cones in the limit are different, but it's in some sense not nice because you don't know how much different are these limit cones. You just know that they are different. And yeah, a bit luckily for us, Jesse and Craig, before we started our joint project, they already started the project on another notion of limit, normalized limits, and there they use tropicalization. And we can use many of the arguments they did and apply also tropicalization to study now in the sense of log limits, the tropicalizations of the PSD and the SOS cones. And then we obtain more quantitative information on how much these cones differ. So we want to tropicalize the dual to the even SOS and the even PSDs. And we now consider only the dual to the evens because we tropicalize something. So we need something which is contained in the non-negative orphan. And we provide then many technical lemmas for the dual to the sums of squares cone and some more lemmas, which can eventually let us calculate the tropicalization of the dual to the PSD cones. And I told you that the image of the Vandermonde map at infinity is a bit complicated. It's not semi-algebraic, and its description is also not that easy. But its tropicalization has a simple description. It's a rational polyhedral cone, and you have two families of defining linear inequalities. And there's also a very good explanation for these two families of linear inequalities, because they are linearizations of binomial inequalities and power sums of the LP norms and of some other series of inequalities. And there's again some correspondence to graph homomorphism densities. And although the cones of even symmetric limit forms are already different in degree 6 and in degree 8, the tropicalizations are still equal. But in degree 10, it occurs then for the first time. We did some calculations in Sage that you have a strict inclusion. And in degree 10, you can compare the H representations of these cones. And in the H representation of the smaller cone, you have actually one more defining linear inequality. And this then can be used to look for examples of limit PSD, but not SOS. Oh, this should be a 10, not a 8, sorry, forms. And yeah, this is one of such examples, which is also in any number of variables non-negative, but for some sufficiently large number of variables, it's not a sum of squares. So thank you a lot for your attention.
Any questions?
So hello, Sebastian. Did you also have a look at the hyperpolyhedral group in terms of constraint polynomial optimization, say, for instance, Laser relaxation? Say, for instance, we have a nice description of Putina's theory for that group.
Yeah. I must say that I could not understand it so well from, you asked about the Laser hierarchy, because there's some good understanding of Putina for BN.
For the group, for the hyperpolyhedral group, yeah.
Yeah, no, we didn't look at this. So we only considered the Vandermonde map, the SOS and the PSD cone. And so in this Putina relaxation, is it the same action of BN that you act as a reflection group with permutation of variables and switching of signs?
Yeah.
Okay, yeah, then it should be, then there should be some results which are comparable or transferable, but we didn't look at it yet.
Okay, thank you.
So what another question? Yes, please.
Yeah, so I have a question. So can you go back maybe to the slide 26?
6, did you say?
26.
26.
Okay, yes. Yes.
Yeah, so just by curiosity, can you give us an idea of how to prove the proposition?
Okay, so we know this test set from the previous slide, or from the slide afterwards, sorry, theorem here. So we consider polynomials in 4 variables, and we want them to be non-negative, but not sum of squares. And then we see that the variable x is arbitrary. This can be in the real numbers. The second variable is 1, and then we have some discrete variable depending on the natural numbers n. And what we then do is we write a univariate polynomial in U. So U is then replaces n here, and this is parameterized by x. So we have family of parameterizations. The family depends on x and r, and then we want that this polynomial has never a 0 when u is a natural number, but we wanted to have zeros when u is in the interval 0 to 1. And then you consider the discriminant of this univariate polynomial, and then you look at it a little bit, and then you see that you only have to consider parts of this interval. So we consider then only the largest part where n is 1/2 to 1, because yes, we consider here 1 divided by n and 1 divided by 4, and then we wanted to have either 0 in the largest part or never 0, and then we do some calculations there to see that this polynomial indeed satisfies that it has a 0 in such an interval, or it has 2 zeros in such an interval, but it doesn't never have a 0 on integer points.
Thank you.
Any other question, please?
Okay, yeah, stay on the slide. Thanks. I'm Giorgio. You presented in a nice way the representation theory of hyperoctahedral as a generalization of symmetric group. No, it's a signed, it's a nice point of view. So I wonder, for the symmetric group, the symmetric polynomials that are the ones in your proposition that have only one representation, essentially not the other pair, they are characters of representation of GL. So you have a duality. So my question is a bit vague. Is there is some other kind of duality that these polynomials are characters of something else?
So now for this hyperoctahedral group, you mean?
Exactly, yes.
Yeah, I must say I don't know, and I must say I should have looked it up, because when I presented this or something related a while ago, there was Christian Krattenthaler in the audience, and he asked the same, or another person asked the same question, and then Christian Krattenthaler interrupted and said that he believes that there should be definitely a counterplay, but he also did not know explicitly. And then I somehow did not look it up afterwards to see if there's some analogies to the true while duality for SN.
Okay.
Yeah, this is Bernd Stompers. Let me take it one step further from Giorgio. Is there any thought of extending any of this to continuous groups, so irreducible representations of Lie groups, GLN?
So what we here really need is the stabilization in number of variables, that you have a fixed degree D, and then the vector spaces have the same dimension. And I don't know so much or enough about representation T with true while duality for GLN to see if there's also a stabilization. So if there is, then I believe with some work there can be generalizations, but I don't know yet. Sorry.
And what about breadth product of SN with other groups? So not only with other.
Yeah, this works, but then when you take these breadth products, then you have complex reflection groups, and then you cannot act on the real polynomial ring, because this breadth product is then not acting by -1, but it's acting by a rth unit root. So you can do analogous start, not really the PSD, but maybe you can consider the Vandermonde. Yeah, but you're in the complex setting for other web products.
Yeah, thank you.
One more question, please.
Last slide about the utilization. So you can show the slide. So you mentioned that only for higher value of n that the utilization is fair. on the retail optimization, you can take image by valuation or image by valuation on sign. Combination from octa, something like that. Which can be registration and
Yeah, I'm sorry, I could not understand it so well.
There are no signs, but everything is in that negative orphan. So maybe I can.
Yes, so for this topicalization, everything is in a negative orphan since we only have even power sums. And then, yes, when you do point evaluations of the even power sums, you end up with something in the non-negative orphan. But I really did not understand the question, I'm sorry.
sometimes you have a final optimization where you consider image by valuation is fine. There's no way to sign optimization.
No, this is just log limit. I can.
Okay,
So I see no more questions. So thank you very much, Sebastian.